let's go ahead and parameterize another surface. This time the surface is the following. It's actually the graph of the function g of x comma y equals x squared plus xy to the fifth. Now, one answer to this question could just be x equals u, y is equal to v, and so then z is equal to u squared plus u times v to the fifth. Here, u and v are the parameters. They are the u and v are the parameters or the parametric variables. But a second answer, just kind of in line with the type of thing that we just saw a moment ago in the previous example, is how about just use x and y as the names of the parametric variables. Okay, and then you'll have z is equal to x squared plus xy to the fifth, and you'll see, I mean, really sort of nothing really much happened here. Now we're just using x and y. X and y are the parameters. Now, in the most traditional sense, we should, I guess, always use u and v to be uniform about things, but you'll see that, instead of introducing new variables, we'll do things like we just saw here. And in fact, based on this, let's take a look at the following interactive question. So does it matter which variables we use as the parameters? When does it make sense to use x and y as your parameters instead of u and v? Okay, let's try another example. Let's parameterize the surface, which is the graph of the function g of x comma y is equal to 6 plus sine of x plus sine of y. Just for fun, you may want to try to think about what this graph ought to look like. Just try to think about it on your own, see if you can figure out what the graph really sort of in a sense looks like. Again, we'll do this thing where x and y themselves will be used as the variables for the parameterization. Then z would equal 6 plus sine of x plus sine of y. Now, we will... Okay, so we're done with that question. Now what? We will parameterize the surfaces obtained as graphs of functions. See, not all surfaces are graphs of functions, but if what you have is a graph of a function, and in this case, use x and y as parameters instead of the traditional u and v. So then our setup would be x equals x, y equals y, and then z is equal to, well, just g of x comma y. Otherwise, it would have been x is equal to u, y is equal to v, and then z is equal to g of u comma v. But while that works, let's not do that. The other way we can write this information is, of course, to have a vector function, right? So r arrow of x comma y equals, well, x comma y comma the z formula here, which is g of x comma y. Now, let's recall that earlier we had said the following, right? If S is parametrized by a vector function r of u comma v equals angle bracket x of u comma v comma y of u comma v comma z of u comma v. So you have a parameterization just recorded as a vector function for u comma v in D, and D here was the parameter domain. It's just a drawing. It's a shape that we draw on the UV plane to let us know what points UV that we take, right? Then in this case, the area of the surface was the double integral over this region D of the magnitude of the cross product of the partial derivatives. So r sub u cross r sub v, magnitude d dA, and this dA was du dv, or it was dv du as appropriate, whichever is more convenient for us. So look, we saw this earlier, and the thing is, we have a special case of this over here right now. We really have, this is a special kind of that. I just got to kind of be careful with some of our notation. So here's this tool that we have. Let's apply it. Just everywhere you see a u and a v, you're just going to have to replace with an x and a y. So let's go ahead and create some computations that are going to help us out here. So taking this r that's up here, okay, we'll switch colors so that we can see what we're doing here. So taking this r right there, then r partial derivative with respect to x is going to equal 1, to differentiate x, 0 to differentiate y, and then the partial derivative of g with respect to x. And then, in addition, r sub y is going to be 0, comma 1, comma the partial derivative of g with respect to y. Then, we won't work out the detail here. You should just do it. If you take the cross product of r sub x and r sub y, you're going to get here negative partial derivative of g with respect to x, comma negative partial derivative of g with respect to y, comma 1. If we want, we could of course write this in ijk form as negative partial derivative of g with respect to x times vector I minus partial derivative of g with respect to y times vector j plus vector k. So if we work out the this magnitude, so the magnitude of r sub x cross product r sub y, okay, we should take the square root of, and then square each of these pieces here, So we should have the square, we'll have square root of, and then quantity negative dg over dx squared plus quantity negative dg over dy squared plus 1 squared. Now let's just clean up how this ends up looking just by writing the 1 squared first, well, just as a 1. So inside the radical we have a 1, and then look, the minus is going to get cleared away by the square anyway, so let's just write this as partial derivative of g with respect to x quantity squared plus partial derivative of g with respect to y quantity squared. So here's the thing. We originally over here would have had so this area of S, which was double integral over D of magnitude RU times RV, cross product RV, take that magnitude, and dA. Let's just go ahead and write here for right now just a du dv to emphasize certain things. This is going to become, this becomes area of S. So we're just trying to apply this in the special case where what we parameterized use the variables x and y instead of u and v, and this specifically worked out so nice because what we were doing was we were parameterizing a special kind of surface. It was the graph of a function. Okay, so then what we end up with is just a special case of this formula. We end up with the double integral over d of, and then this turned into that radical thing here instead. So we have here double integral over d of the function root 1 plus partial derivative of g with respect to x squared plus partial derivative of g with respect to y quantity squared. And then the dA here will now be a dx dy or dy dx. So we'll just write a dx dy just to emphasize how it's different from a du dv. That's really all here. Okay, so this is the formula you can use where S is the surface that's just given by z is equal to g of x comma y. So you have a function called g of two input variables, and it's just this is just a special case of this area formula that we have right there. Okay, so let's just again really point out carefully what we have. So if we just, sorry, this is going to get messy across the page line, so I'd just like to do this. Copy, paste this down. Oh, that did not work. Let's just do that and then come here. And let's just point out what's going on with these two things. Okay, so over here, we have, this is the area of a general parametric surface. So when you just parameterize any surface, parametric surface, you can always use this top formula. But then a special case of this, right? This is the area of the graph of a function. G of x comma y. So the first kind you can use on any kind of surface, but if your surface happens to be the graph of a function called lowercase g of two input variables called x and y, then you can set it up this way again. But this second formula just grew out of the first one. It's just a special case. So this one over here, this first formula, this is what always works. I mean, of course, you have to have a parameterization of your surface, whereas the second one here, this is only for the graph of a function.